Hello, those of us joining us on YouTube. Lab this afternoon, that's full lab attire. Even though after that lab finishes, we'll then switch, will we switch to the classroom or will we stay in the lab? We might actually have to stay in lab depending on how well we can social distance, because it's going to be a lot busier than we normally get for lecture. So we might still be in lab, but people can start working on the experiment number 5, which is a dry lab anyway. Okay. So we finished on Friday with the nomenclature of covalent compounds. We said that the more metal-like element is listed first. That's the one further to the left or closer to the bottom, closer to that metalloid divide. And the name of that element is left unchanged. It's the latter element which changes to the IDE ending, just as we did in ion chemistry. And then the one real change from ion chemistry when naming the compounds is that we now do want to know how many atoms are in the chemical formula. So as we said at the time, PCl3 for phosphorus trichloride, or B2H6 for diboron hexahydride and all that. So we need to know how many atoms are in the chemical formula. So let's take a look at chapter 4, continued. Now we want to talk about the shape of molecules. Each central atom, of course, is surrounded by electrons to make up its octet. And that octet of electrons, whether it's lone pairs or bonding pairs, are made up of these negatively charged electron pairs, which don't like each other. They want to get as far away from each other as possible, like three mortal enemies who all came to the same birthday party for some reason. They would keep their distance from each other and kind of circle around each other in the room. So if one person moved to the left, the other two would have to move to the right, and so on, because they're trying to keep their distance from each other. It's really just like, I might have gone over this quickly on Friday, this analogy of satellites around the planet. Satellites that start to appear in the latter part of the 20th century. Because the Russians got their one up first before the Americans got one up. So let's see, let's use green for the planet while it still is green. My trusty pen. So we've got the planet Earth. And then around the planet, we've got these satellites appearing. First satellite goes up, doesn't have to worry about anybody because there's no one else that it could collide into. When the second satellite goes up, if it's a prime directive to keep away from the other satellite, almost as if they were repelled by each other, like electrons are repelled by each other, while still being in orbit around the planet, like electrons in orbit around the nucleus of that central atom, their positioning would be like a straight line through the planet. They would be linear through the planet. Oh, because I have to take this off now. Oh, I don't. They say talking to yourself is the first sign of madness. Although I guess as long as you don't answer back. That's a dad joke. So if we then switch to 3 satellites, which are trying to avoid each other, just like 3 sets of electrons trying to avoid each other, they would triangulate to give this trigonal planar shape, or triangle shape, we'll just call it for now. That makes sense. Likewise, if we switch to 4 groups around the planet, 4 satellites, they would still be spacing out as well as they could, getting as far away from each other as possible. So we have the points of a square on its side, admittedly. Alternatively, if we have 5 groups around the planet or 5 satellites around the planet, they would space out from each other as evenly as possible. There's Alex. Space out as evenly as possible. So they would take up the points of a pentagon with 5 sides, drawn badly, of course. So we'd have a pentagon. Or if we had, oh, there's Dylan as well. Or if we had 6 groups around that central atom, again, spacing out as evenly as they could from each other, we'd get the points of a hexagon, a 6-sided shape. So just as it's potentially a governing rule for these satellites to get as far away from each other as possible, it's a governing rule for these electron pairs to get as far away from each other as possible. And so if we can predict how the electrons repel each other, we can predict the positioning of those electrons around the central atom, and therefore predict the shape. And that's exactly what we do with VSEPR theory. Valence shell electron pair repulsion theory. The valence shell electrons, that's the only electrons involved in chemical bondings. And the other electron pairs, whether it's bonding pairs or lone pairs, and it's how they repel each other around that central point. The only little extra qualifier, the party's getting bigger, excellent. Here comes Mackenzie. So the only clarifying statement we have to make about these electrons around the central atom is that when it comes to double bonds or triple bonds, we treat them like one single entity. Here, 2 atoms bonded together by overlapping the shell, and whether it's 1 bond, 2 bonds, or 3 bonds, they have to occupy the electrons, they have to occupy that mutual space between the 2 atoms. And so double and triple bonds are treated just like one single bond. They're locked into that space together. Now, of course, they don't like being cramped in together like that, and that does increase the energy of the bond, but we'll talk about things like that in a later chapter. So let's look at some of the shapes that we can get. Unfortunately, I don't have a molecular model, but we'll look at these this afternoon and spend a quick 20 minutes going over these 2 pages, just 2 pages of shapes to work out. Now the C here is for central, it's not necessarily for carbon. But the idea with this first one is that we've got 2 sets of electrons around that central atom, and then some black atoms or some kind of atom is connected on the other side of those electrons. Now, of course, because the atoms need an octet, if there's just 2 sets of electrons, that's got to be either a single bond and a triple bond, or 2 double bonds. It's got to be an octet normally. And then we talked about boron and beryllium, which sometimes break the octet rule. But hydrogen cyanide was the very first molecule that we drew, so we're aware of that and familiar with it. Likewise with the silicon dioxide, that was one of the early Lewis structures we drew last week. And so we're aware that the silicon and the carbon both have an octet, and then make that up with just 2 chemical bonds, single and a double, and then 2 doubles. And those 2 bonds get as far away from each other as possible, so they stretch out to opposite sides of the atom, and it gives us this linear shape. I did find a web page that we could look at that for. Whoops. Let's see, expand my diagram. So we're just looking at this picture on the left here, and you've got your central atom. You've got some unknown other atoms about the central atom, and they occupy the space, those bonding electrons, on opposite sides of the nucleus of that central atom. Let's see, we can show the molecular shape of this. So there's a carbon in the middle, or maybe the silicon in the middle if it's silicon dioxide. You've got those two red oxygens at either end, and it's a double bond holding the molecule together. So wherever one bonding pair of electrons is, that one double bond, the other double bond is always on the opposite side of that central point, that central atom. And so it creates this linear shape. Everybody see this, what I'm pointing to?
Yeah.
Okay, so the video is working on your screen as well. Sometimes it does weird things when I'm trying to do something, excuse me. Oh, that's a great cup of tea. Right. So with two sets of electrons, we get this linear shape. Now, if we add in another pair of electrons to make 1, 2, 3 chemical bonds around the central point, the electrons have got to move because they've got to get as far away from each other as possible, because electron pairs are repelled by other electron pairs. And so we make up the points of this triangle in these three positions. Let's see, where's my pen? Okay, so from one outer atom to the next, we've got the points of a triangle. All the atoms are flat with the table, they're in the same plane. And so the name we give to this shape is trigonal planar. Trigonal planar because it's in the points of a triangle and they're all in the same plane. And again, we've already looked at some example molecules like this. We looked at things like the phosgene Cocl2. It's one of the Lewis structures that we drew last week. Again, we can pull up our video content to show that. We've got the central atom here and 1, 2, 3 atoms surrounding it, connected by covalent bonds. So 1 bond, 2 bond, 3 bonds. And just remember that one of these 3 bonds must be a double bond because there's got to be an octet, and we just treat the 3 bonds as 3 separate entities. So those 4 electrons making up the double bond are just treated like one group. So we get this trigonal planar shape, and as you see it turn there, it's flat. Whoops, I missed it. It's flat with the page or flat with the monitor screen. There we go. All in the same plane. And it takes that shape just as the linear molecule took that shape because it keeps those electrons as far away from each other as possible. Maximize the bond angle, we minimize the energy. So our linear is 180 degrees, while for our trigonal planar, if I stop it, from one bond to the next, that's an angle of 120 degrees. 1/3 of a circle, 360. Any questions so far? We're doing okay? So trigonal planar and a bond angle of 120 degrees. Now, if we were to chop off one of the atoms and turn that bonding pair into a lone pair, notice that the electron positions doesn't change. They're going to stay in exactly the same positions. Now we have looked at a molecule like this already. I think we did nitrate as one of our Lewis structures. And there's a lone pair with 2 bonding pairs, one of the bonding pairs being a double bond. And they're still stretched out 120 degrees from each other, keeping those electron pairs as far apart as possible. But when we think about the shape, there's no longer anything physically out here on the right side of the molecule. Whoops, stop it. Hate it when it does that. So there's nothing on this side. It's just empty space apart from that pair of electrons. So with nothing on that side to look at, we now say the molecule is just bump, bump, non-linear, or sometimes described as being bent because of that non-linear shape. And it's the lone pair repelling the bonding pairs which creates that kink, which creates that zag to the molecule. Now if we take another bonding pair and strip it of the atom it's connected to, turn it into another lone pair, so I guess this one turned into a lone pair, we now just have two atoms connected by a straight line, connected by that double bond, and so the molecule just becomes linear at this point. And there's no bond angle associated with it because you need 3 points, 1, 2, 3, to create a bond angle, and we just have 1, 2. So the molecule automatically becomes linear at that junction with no bond angle. So halfway there, two chemical bonds, they are separated by 180 degrees, and we say that it's linear. 3 chemical bonds, we now call it trigonal planar, and are separated by 120 degrees. 2 bonding pairs, they're still separated from each other by 120 degrees, but because there's nothing on the right hand side, it's just now non-linear or bent, and then linear for the last one. All of these molecules are examples where the molecule is flat. What we're going to look at in a moment, when I see what my daughter is yelling about, is molecules which are spaced out in all 3 dimensions. So we no longer have molecules which are flat with the page. One sec. In fact, let's make it a 5-minute break because we've been just about halfway through our time anyway. So if you need the bathroom or want to grab a drink, now would be a good time to do so. They've probably run out of popcorn. They're watching the Teenage Mutant Ninja Turtles right now. So let's look at the second batch of shapes we have, just 3 of them. And we've got a problem because with 4 chemical bonds around that central point, the electrons are starting to get squeezed up. So let me show you something quickly that doesn't happen. We might be tempted to think that the bonds space out flat with the page like this, making up the points of a cross. Looks reasonable, but the bond angle from one pair of electrons to the other would only be an angle of 90 degrees. That's starting to push the electrons too close for comfort. If you imagine my hands as a pair of bonding electrons, the smaller the angle, the closer the electrons are to each other. So we've got to maximize that bond angle to minimize repulsion. And the shape here, with a bond angle of 90 degrees, doesn't really cut it. It's not the maximum distance, the maximum angle between the electron pairs. So the bonds elevate up into that 3rd dimension off the page to create this trigonal, this 3-sided pyramid structure, what we'd refer to as a tetrahedron. And this maximizes, so there's like the side at the back there. So just a 3-sided pyramid, and we're saying that the central atom is actually buried at the center of the pyramid, like the Pharaoh's tomb. And this tetrahedron structure creates a much bigger bond angle between the bonding pairs which are connected up to the central atom. It creates an angle of 109.4 degrees, or just 109 for short, just being a bit nerdy, putting in the 0.4 there. We've seen a couple like this. We've seen phosphate, with 1, 2, 3, 4 chemical bonds. And at some point, I think we also did carbon tetrachloride with 1, 2, 3, 4 chemical bonds. So we've already seen Lewis structures which match this criteria. And these are molecules which would be considered tetrahedral, with a bond angle of 109.4 degrees each time. Again, let's pull up our web page to look at this. They do it very nicely, I must admit. So the grey there is for the central atom, right at the center, and then we're looking to the 4 atoms it's connected to, each one in the corner of that 3-sided pyramid. So let's look at the shape, a tetrahedral shape, carbon at the center, and those 4 chemical bonds stretching out as far as they can from each other. And they make up the points of like a tripod stand with a flagpole coming out of the top. Oh, it looks like the tripod stand is oh, I can do that. Look at that. Hey, one sec, guys. Okay, you get one kid milk and then the other kid wants milk too. I didn't know I could do that. Look at that. Wee. So we've got kind of like a tripod stand, and then there's this kind of support beam at the top where you'd mount the camera onto, I guess. And those 4 chemical bonds are getting as far away from each other as possible. If I stop spinning there, you can see how that angle for every single bond is a little bit bigger than 90 degrees. So it's maximizing bond angle to minimize repulsion. It doesn't matter which way we turn it or which 2 atoms we look at, we still see an angle which is bigger than that 90 degrees, an angle of 109.4 degrees. So that's a tetrahedron, or a tetrahedral as we call it, when we have 4 chemical bonds around that central atom. Now, if one of those chemical bonds is removed, one of them becomes a lone pair, we basically get rid of the atom at the top. Notice that the electrons, just as we went from trigonal planar to nonlinear, the electron positioning is exactly the same. That's because they're getting as far away from each other as possible. But now, with that lone pair at the top, there isn't anything physically connected at the top there. So it's a little bit like the tetrahedron with the top sawn off or truncated off. See, let me use red for this. So while the pyramid used to stretch up here like that, and the side around the back, we have sawn off the top of the molecule. So this bit does not appear. And that's why in Britain, with that top bit sawn off, we would actually refer to this shape as truncated tetrahedral. Frankly, it's a term I prefer. I think it's more descriptive of what's going on because we've sawn off or truncated off the top of the molecule. So it's sometimes referred to as truncated tetrahedral, although in America, you're more likely to hear trigonal pyramidal. I prefer that term. It probably makes more sense, I would say, compared to trigonal pyramidal. So either term is fine with me. However, that lone pair is being held closer to the nucleus because the electrons are not being fought over with another atom. This guy isn't there anymore. And so that electron pair is held closer, and so it repels the bonding pairs a bit more strongly. And so the bonding pairs huddle closer together than they would be when there was 4 chemical bonds. The lone pair is more repulsive. And so the bond angle from one bond to the next and one bond to the next is now just 107 degrees. If we take it a step further and put in another lone pair of electrons instead of a bonding pair. Our last shape, so that bond there turns into just a lone pair and we lose this atom. Notice especially it's still that tetrahedral arrangement of electrons because that's getting as far apart from each other as possible. But because lone pairs are more repulsive than bonding pairs, the two remaining bonding pairs have to squeeze slightly closer together. It's like you've got two mortal enemies at a party, but one of them, is just, I don't know, some issue like maybe a loan of $5, while with the guy on the other side, it's an issue of a loan of $5,000. So maybe you stand a little bit closer to the guy you owe $5 to because there's probably less friction. And it's the same with these bonding pairs. Although it's creating friction by getting closer together, it's less friction overall, less repulsion compared to standing closer to the lone pairs. Lone pairs are always more repulsive than bonding pairs. So that remaining bond angle between those 1, 2, 3 atoms, the angle goes down to 104 degrees. So it's pretty regular, from 109 to 107 to 104 every time we add a lone pair. Any questions about those? We're doing okay? Now, as we did last time in class, oh, there's a nitrate I was talking about. Oh, no, that was nitrate. Just as I did before, although I've drawn in the molecules here, I'm just going to quickly take 5 minutes or 10 minutes to draw the molecules from scratch. That's probably a better learning tool. Excuse me. Right. So let me clear this out of the way. And we'll build this molecule from scratch. So we've got carbon dioxide, CO2. And of course, like we said, the first thing we do is just count the valence electrons for the molecule from the position of the elements in the periodic table. See, I should have a periodic table here. Yep. For carbon, it's the 1, 2, 3, 4th element in the second row. It's got 4 electrons in its second shell. Oxygen, it's the 1, 2, 3, 4, 5, 6th element in the second row. It's got 6 electrons in its second shell. And so 6 electrons for each oxygen, 4 electrons for the carbon. We get a grand total of 16 electrons. And we'll use exactly 16 to build the molecule. Choosing the central atom, of course, carbon needs more electrons, another 4 with the 4 it has to make an octet. Well, each oxygen only needs 2 electrons together with the 6 it has to make an octet. So carbon needs more electrons. It would be expected to make more chemical bonds. That's what we call the combining power, we said. Electrons needed normally suggests the number of chemical bonds. We do sometimes break that rule, but it is a good starting guideline. That takes us down to 12 electrons. We'll use the remaining to fill octets, starting with the outer atoms. And that uses up our supply. And of course, we still don't have an octet for the carbon in the middle. It only sees 2 bonds, 4 electrons. So we're going to borrow a lone pair from this oxygen, turn it into a bonding pair. That gives it 2, 4, 6. We'll borrow another lone pair from that other oxygen and create another bonding pair. Now the carbon sees the octet it needs, 2, 4, 6, 8. Shell's complete. We've finished the Lewis structure. The 2 sets of bonding electrons get as far away from each other as possible, basically opposite sides of the atom. And so we get this bond angle of 180 degrees. And of course, the molecule is linear. And it doesn't matter which elements you have, which atoms. If it's the same combination of bonds and lone pairs, it'll be the same shape every time. That's the nice thing about it. Let's pull that one back. Any questions? We're doing okay? Again, let's build the sulfate up from scratch. That's better to work on it like that. So for the sulfate, SO4 2-. Of course, this is one of our polyatomic ions from chapter 3. And we've got 6 electrons for sulfur, like oxygen, 6 element in its row. And then we've got the electrical charge itself. It's negatively charged, which is telling us about a surplus of electrons. The more electrons you have, the more likely the molecule is going to be negatively charged. So 2 more. That gives us a total of 32 electrons. Choosing the central atom, both sulfur and oxygen need 2 more to make an octet, but sulfur is lower in the table. It's a physically bigger atom. So sulfur goes to the center. We connect it to those 4 oxygens using 2 electrons each time, of course. So we're down to 24. We'll use those electrons left over to complete the octets of the atoms, starting on the outside first and working our way in. Never add electrons to the central atom unless there's nowhere else for the electrons to go. And that uses up our remaining supplies, 6, 12, 18, 24. Now this could be the final answer because the sulfur does have an octet, but of course we know that sulfur is one of our hypervalent elements. Uh-oh, you just keep them in your bowl, okay? I'll give you a drink in a minute, okay? Because there's the popcorn they're being eating to watch Ninja Turtles. It's hypervalent. And we said that phosphorus can have 8 or 10. Sulfur, excuse me, can have 8, 10, or 12. And chlorine, the last of the hypervalent elements we look at, can be 8, 10, 12, or 14. Each atom takes it a step further than the last. They raise the stakes by 2 electrons. Raise the stakes by 2 electrons. So sulfur sees 2, 4, 6, 8, but maybe it'd be better with 10 or even 12 by drawing extra bonding pairs. We'll find out if we need that by checking for formal charge. That was the periodic table position compared to the share of electrons in the Lewis structure. So let's do the oxygens as well. They should control 6, we'd already worked that out. And each of them controls 1, 2, 3, 4, 5, 6, and 1 of the 2 electrons in the bond. So we get an answer of -1 for each of those oxygen atoms. And that's always the answer for oxygen when it's got 3 lone pairs and 1 bonding pair. Now the sulfur, which we're really interested in, it should also control 6, but it controls just 1, 2, 3, 4 of the 8 electrons around it. Remember, these are shared electrons. So there's a charge on the sulfur of +2. And we need to get rid of the charge on the hypervalent element itself. Get rid of that charge. So we are going to use its hypervalency by taking away a lone pair and turning it into a bonding pair. That gets rid of the charge on the oxygen. It should control 6, and now it does, so no charge. And the sulfur now controls 5 of the 10 electrons around it. And so its charge diminishes down to just 1 plus. We still have room to add more electrons because the limit for sulfur is 12. We've only got to 10. We can go up to 12. So if we take another lone pair and turn it into a bonding pair, with that's a terrible double bond. With 2 double bonds, now the sulfur controls 6 of the 12 electrons around it. 2, 4, 6, 8, 10, 12. Remember, each bond, each line is a pair of electrons, and these are shared with the oxygen. So 1, 2, 3, 4, 5, 6 electrons belong to the sulfur. So get rid of the charge on the sulfur and rid of the charge on that other double bonded oxygen. So that's our final Lewis structure because we've got rid of the charge on the hypervalent sulfur. And that's within our limits of hypervalency for sulfur. 1 sec. Again, a bit impatient for lunch, I suspect. Okay, any questions about that one? We're doing okay?
Yeah, we're good.
All right. Someone wrote in one of their lab reports the other day, I don't understand this at all. And to which I wrote back, why didn't you ask me? It's normal for you to not understand aspects of the chemistry. That's why you ask questions. Like when you're ill, you talk to your doctor. Or when you've got financial problems, you talk to your bank or your financial advisor. Do I have to go on? When you've got problems with siblings, maybe you talk to a psychiatrist or something. You talk to these professionals. Right here. Just find something which you don't understand, take a picture, send it to me and say, I don't know how to do this. That's great. We've got something to talk about. That is what is missing for a lot of people just now. They're not giving me feedback, not talking to me about their problems. And I want to hear about your problems. That's my whole job, at least a big part of it. Anyway, griping over with. Let's try this one, and that's probably as much time as we'll have left. That's not bad. So again, we'll just quickly go over it. Oh, hang on, just quickly. Of course, so we've got 1, 2, 3, 4 chemical bonds around the central atom, and we said that was tetrahedral with a bond angle of 109.4. Don't be put off by the way I've drawn it. It's just easier to draw like this, but of course, really for that tetrahedron, there would be 1, 2, 3 of those bonds like a tripod stand below the sulfur, and then one of the bonds would be coming straight out the top, together with lone pairs of electrons, of course. The oxygens make up the points of a pyramid, a tetrahedron. Okay. So let's look at the nitrate. That will finish things off for us today. So remember, lab at 2, full proper lab attire. So nitrate, again, rather than just look at the picture, let's build up the molecule from scratch. It's good practice. So for nitrate, NO3 minus, we've got 5 electrons for nitrogen because it's the 5th element in the second row. Then oxygen next door, the 6th element. There's 3 of them. And then the charge, negative, telling us there's 1 more. So electron count this time comes to 24 electrons. Choosing the central atom, nitrogen needs more to complete its octet of 8. So we put the nitrogen at the center and surround it with the oxygens. That's used 2 electrons each time, so we're down to 18. We'll add lone pairs to complete octets. And that uses up our supply. All done. But we still don't have an octet for the nitrogen atom. So we'll take a lone pair from one of those 3 oxygens, doesn't matter which one, and we'll turn it into a bonding pair. Now the nitrogen sees an octet. We've got formal charge. Of course, the oxygen should be 6 electrons, but it's 7 with just 1 bond. So -1 there, -1 there. And we've got a charge of -1, which should be the collective charge in the molecule. And it's pointing to the fact that the nitrogen, which should control 5, only controls 1, 2, 3, 4. So there's a +1 charge on the nitrogen as well. And we can't get rid of that because it's in the second row. It only has 2 shells. It's not hypervalent. It does not have access to 3D subshells to store electrons. So we're done. That's it. But overall, -1, +1, -1, -1 overall. Those 3 bonds stretch as far as they can from each other, and that gives us the trigonal planar shape. Nitrogen doesn't like having electrical charge, and it's really bad having positive and negative charges right next door to each other. That is destabilizing, but completing the octet gives enough stability for it to exist. But the charges are a problem, and that explains why nitrate is actually so potentially explosive. You're halfway to TNT with nitrates. And then of course a bond angle from one bond to the next, bond angle of 120 degrees. Okay. Any thoughts, any questions come up? Doing okay? All right. I'll see everybody this afternoon in lab. Stay safe, wash your hands, wear that mask. And just like that, they all left Dr. Elliott. He was alone.